So we've heard from the research side, we've heard from users of technology, and thought it would be good to round out our panel with someone who is involved in developing technology. So I'd like to invite Doug Schillinger from RBR.
All right, so I'm Doug Schillinger from RBR, and when I developed this talk, I tried to play up a little bit more of the collaboration side than just a profile of RBR, but our collaboration, of course, is all product development, so it's hard to remove the two. I think a lot of some of the things that I say overlap with some of the talks from this morning, particularly Krish and Bruce, in terms of what collaboration means, how do you make it work, and essentially about trust. I think Krish brought up in his opening speech. So my talk's going to start a bit about me before I get into RBR. So I started my career doing, I guess, my master's out of Memorial. So I also did time out there, although I don't know that I'd refer to it like it was a prison sentence, Bruce, doing time in St. John's. And I also got screeched in while I was out there, originally from Ontario, and moved out right after the ice storm that shut down Ontario and Quebec back in 97, 98. I worked on wind observation through ambient noise, so that itself was a collaboration. Len Zadell was working with RDI, as it was at the time, now Teledyne RDI, to add a hydrophone in and record ambient sound in the water and tie wind speed measurements in with velocities made from the acoustic Doppler profilers. When I finished there, I worked with Brad DeYoung for a little bit and then moved to Halifax to work with Alec at Dalhousie University. Initially, for again a collaborative project in the Bay of Fundy, monitoring right whales. And we worked with Mo Brown as well. Chris Taggart was the biologist involved from Dal, and Alec was the physical oceanographer. Defense Research and Development Canada was involved. They were known as DREA at that point. And the focus was on coming up with a real-time observatory for identifying and tracking right whales. That project ended up getting shifted to narrowing the shipping lanes going into St. John Harbour to help mitigate right whale collisions. At that time, we were also developing a real-time observatory in Lunenburg Bay for the Center for Marine and Environmental Prediction, right around the same time that GOMOOS was coming online. From there, I ended up working on Dal's contribution to the Neptune Canada project, and I worked on an Atlantic Innovation Fund project there as well. So the reason why I bring that up as I lead into what RBR does is RBR is an oceanographic company in Ottawa, in the dead center of the continent, as far away from the three oceans as you might possibly get. It's a spin-off of collaborations with the National Research Council, which is the history behind why an oceanographic company is so far from the ocean. But it's comprised of employees who are people like me, who have spent time in academia doing research, putting instruments in the water, and have a real interest for how to get the best measurements out of the instruments. It's not just a matter of getting instruments for the lowest cost in people's hands, but making sure that those instruments do the things they need to do. RBR stands for Richard Branker Research. He was a consultant, founded the company in 1972, and got contracts from the National Research Council. One of them was to make a thermistor string for the Great Lakes research. And around the time they finished that project, an engineer left the company and went to work on artificial hearts at the Cardiac Institute in one of the hospitals in Ottawa. But in the early 90s, he came back to the company as Richard was getting ready to retire. And instead of having various odd projects that they had worked on through the years with no real skews, they decided to focus on the thermistor string. And Frank rebranded as RBR in the late 1990s and focused on the calibration facility that they'd been building over the years. And focused on oceanography. So we make high-precision instruments for oceanographic research. So that focus in the early 2000s was on calibration and getting calibration for conductivity, temperature, and pressure to the sort of highest levels we can achieve within sort of the noise bounds inside a lab. So our instruments are calibrated to World Ocean Circulation Experiment, WOS standards. And they're good for harsh and rugged environments. You can see we've talked about working in harsh conditions. This is I think, a glacial lake in the Antarctic. The divers there were deploying one of our sensors for long-term deployment under ice. We like to say freeze our CTD. It's a rugged instrument. So our products are CTDs, conductivity, temperature, and depth sensors, as well as dissolved oxygen, fluorescence, redox potential, pH, PAR, I think what Neil referred to as all that other stuff. And having experience in physical oceanography, I understand that it's all that other stuff, but that other stuff isn't of interest to a lot of people. So who would use our stuff? Well, the academics like Neil and other people, or Stantec, or I'm not saying Neil does use our stuff, but people like Neil might use our stuff. Universities across the country and in North America as well as worldwide. So we have sales worldwide, with half of our sales throughout China and the rest of the world, and half in North America. We make thermistor springs, tide and wave gauges for coastal engineers and people doing sediment transport, to biologists measuring temperature profiles in the Great Lakes, or for aquaculture groups and other places. We're a modular platform, so our logger is built on a base core that we just add more serial boards or analog boards to, and we can build it up. What we focused on is making that low power, so that when it's off and it's not sampling, it's not drawing a current. And we put lots of memory on board. And so in the industry, there hasn't really been a race to lower cost for sensors. It's been something that's an established trend. But what we can do is make incremental improvements to the sensor by getting more. And so there, we're reducing your cost per data point. Now, is more data always good? I don't know the answer to that. We certainly think it is, and lots of people are pushing that way, but people are building up data repositories. But we find more and more, because of the cost of deployment and the cost of getting out on a boat, to have an instrument last longer or collect more data is certainly something we can put in your hands. So that's RBR and headquarters in Ottawa, but of course this is an Atlantic conference, and so I'm based in Halifax. I'm the Atlantic office, and we have RBR Atlantic, which was created to foster collaborations between the ocean tech community and between ocean institutes. And my colleague on the West Coast is Chris Contos. He also has a similar history as I do. He worked for the University of Hawaii, doing similar things, putting instruments in the ocean. And then he switched from there to work for Nortec USA, which makes acoustic Doppler profilers. So some of you may know Chris from his 2 years at Nortec. And he's moved back out to the West Coast and is working for us and collaborating with Scripps and APL, University of Washington, and other institutes like that. And this is a shot of Halifax Harbor taken from my phone and a panorama, which is why the image is bent like that. But this is one of the things we have access to in Halifax that we don't have access to in Ottawa. And one of the reasons why we sometimes need to collaborate with institutes is to get our loggers in the water and measuring things. I think Nate said from ORPC that you really start learning when things are in the water. It's one thing to calibrate your sensors to certain standards in the lab, but you really need to make sure that they perform well dynamically. So you can see in the distance there one of the two bridges in Halifax Harbor, and off in the distance is Bedford Basin, where the Bedford Institute of Oceanography is. So now we get into kind of the meat of the presentation in terms of what collaboration is and how we collaborate. Is it just selling one of our instruments off the shelf? Is that collaborating? You know, from some sense I might want to say yes, this is a small community and everyone who's working on something is doing something innovative and interesting. I don't think that really qualifies in this sense, but that is how our products develop, is in our interaction with customers. So talking with someone from another field, they asked me about sales, and they said, well, surely you have someone for inside sales that you just pass your one-offs for. So we make temperature sensors, they're $600. And I said, no, I handle that as well. Every sensor I sell involves a conversation in terms of how people are going to use it, what they want to use it for, and how we can improve it. So, you know, in a sense, that is collaboration, and that's how we move this improvements in ocean tech. But beyond that, it's the customer service. It's selling them one and then having them come back to have a bigger project and say, you know, that worked really well. What if I buy 100 of them, and how do I get that data back in real time? And now we're starting down the road of how to collaborate. We also develop internally. We have research and development, and we're tied closely. Our sales team is myself and Chris, and a research scientist who I worked with at Dal, and then he was a postdoc at Hui, and now we've hired him as a research scientist to make sure that the sensors we put in the water are working well. And so that team works with our research and development team in coordination with customers. So we don't prevent a barrier as a sales team to talking to the engineers. We'll give you their phone number, and you can talk to them directly, because that's where the real collaboration comes, when your engineers are talking to our engineers to make sure the integration of whatever it is we're talking about works well. Whether it's a new sensor you're working on in hand to measure concentrations for trace metal, which is something that's still not widely available or available at all in situ, or some other development, it's great to be able to put it on our logger where we focus on what we're good at, and that's low power, high memory platform for sensor development. So we can do that internally. We also do it company to company. There's a lot of shifts in the marketplace which are creating a need to put alternative sensors on platforms where, say, one manufacturer has been dominant in the market for years. And we'll get to some of that in some later slides. Maybe a university with our company wants something like the telemetry system you were talking about earlier in terms of a buoy for getting data back with telemetry. Or sometimes we have a need where we need to get something in someone else's hands to test. And I'm going to end the talk with us in a tower tank at Woods Hole Oceanographic Institute. So in collaboration, how do you make that work? And I think we've talked about that. You need to build on your partner's strength. There's no sense in duplicating something that's already been made or trying to partner with someone who you have the same skills as. You need to take advantage of who it is you're working with and that unique set of skills or unique set of infrastructure, whether it's on our end or whether it's on your end. And then in the end, you need to really make sure you define what you want to come out of that. So I know I've been involved in projects where companies have asked an academic institute, or I've seen it from the side, there's not really a clear deliverable, and then both sides walk away unhappy, and that doesn't work well for developing ocean tech. And I think the real trick in making that work is having trust and a strong working relationship. There, of course, will be disappointments along the process, but as long as you have a plan in place to overcome them, collaboration works really well. So who do we collaborate with? These logos don't necessarily mean that they're an endorsement, but they're working with us and we're having products. So this logo here is MRV. They make an Alamo Float. They have our sensors integrated directly on their float. Their strength is in the profiling engine. Our strength is in the sensors in the logger. Again, it comes down to cost per data point. Where we're low power, they can get more profiles out of a single deployment, more measurements out of their lifetime, and so they reduce the cost for data. Teledyne Web is also working with us to get our CTD on their profiling platform. MetOcean has our temperature and depth on one of their floats and our CTD on others. And we're working strongly with the Argo community to get our sensors qualified and integrated into the Argo community. So Argo is a network of drifting buoys that are deployed and last a number of years and collect profiles through the water column in the deep ocean. And that data gets moved to a database. Because it's measured against historical data, you need to make sure that whatever sensor you have on that platform meets very rigorous standards. I have the Atlantic Canadian Opportunity Agency here, listed up here as well. That's ACOA. They run an innovation fund, so we're often entering letters of support for researchers and working with them on new developments. And I have Delmar Oceanographic up there, which likely no one has ever heard of. It's a new company that's been spun out of Scripps, and they have a wire walker technology, which is something we worked on them with, and we'll get to that in a slide. An early integration that I was involved in when I first started at RBR 3 years ago was this project with Earl Davis. It was integrating a Paris scientific sensor into our logger, and this is one of those head scratchers. Is it really a collaboration, or is it just a new product, just an off-the-shelf thing? Paris Digicourse pressure sensors have been around for a long time. They're very stable and they don't drift in comparison to a Druck or Keller pressure sensor. But the collaboration here was the Institute of Ocean Science out of Victoria had developed a special counting algorithm for that, and we've ended up integrating that counting algorithm. So we get parts per billion resolution out of this sensor, and that's millimeters and kilometers of water. So it acts as a tsunami meter or seafloor compliance. And working with Earl, Earl has a long history of working with boreholes and the ODP, Ocean Drilling Project. And so we've gotten a lot of knowledge out of him in this collaboration, and working with him has certainly been fantastic. We're working on a new product, on a 3-axis accelerometer for him, for a project going forward for some new boreholes. Having left DAL 3 years ago, there was professor who's now down at Virginia Tech, but she was a postdoc for Alamo, and she worked with, well, on her own project. She is focused on sediment cohesion and how sediments start to become mobile as wave and tide action rolls over top of them, and Alec is a sediment transport guy. So you see in the top, well, your top right-hand corner, there's a frame there with some other instruments on it. They're not RBR, that was a separate project. That was a new Doppler for measuring bed load. But you can see we're in the, on Advocate Harbor, right up here in the top of the Bay of Fundy, with a huge tidal excursion, so a 10-meter tide, and we had a huge access to a beach where it was out of the water for half the day and then underwater for a large portion. And you can see it was quite rough and active there. But Nina Stark from Virginia Tech buried our sensors, which is a non-standard application of an off-the-shelf sensor. And she wanted to measure the pressure phase between the water and the sediment. So you can see on this side, this is just one of our sensors strapped to a block. That was Alec's off-the-shelf instrument he had lying around. She wanted proof of concept. That proof of concept turned into a can I sample faster question. We decided, well, yes, sure, we could. And now we've added a new feature for our logger, the smaller one you see there on your right-hand side, the duet. So we broke our 2 hertz sampling barrier and got it up to 16 for Nina. We were talking about John Grant. John Grant has a research chair, and John approached me and said, I want water quality measurements on site and at a reference site about 500 meters away from one of the aquaculture sites. And I want 2 telemetry buoys from that data. And I said, well, why 2? We make a mooring line modem. Why not just run a jacketed steel cable to connect all your sensors and run it up through one buoy so you can have that where the feed barge is. So there's Nova Scotia. The red dot is Liverpool, where the site is. A zoom in on Liverpool, and the site is just off this island here. And another zoom in, and you can see, well, maybe you can't see, but these are the pens here. So we put together our sensors, which were off the shelf, but we also made a data acquisition system and telemetry system on the surface, and worked on that with John. Now, things changed a bit in terms of the implementation and what site it was going to be at, and whether or not there was going to be a feed barge. The feed barge has moved, so John's sensors are out, but the surface telemetry is looking for a new platform currently. But one thing leads to another, and that telemetry system and mooring line modem worked well with something that the guys at Scripps were working on, and that's this wire walker. So they have a surface buoy and a jacketed steel cable and a traveler that moves up and down that jacketed line. It works on wave action. The wave action at the surface drives it down, it ratchets it down. When it hits this metal plate, it releases the ratchet, the buoyancy brings it up, and it profiles through the water column. So our sensors make a point measurement, and you can either deploy them, leave them in one spot over time and get a good long time series, or you can profile through the water column. It's pretty typical, the 2 means of operating these sensors, but the profile gives you only one measurement in a point of time. So this wire walker, and there are many like them. Bedford Institute has one, McLean has one, PMEL has one, will either drift or be moored and collect that profile data over time. And so you can see our logger here, and our mooring line modem is what drives the data up to the surface. We made the integration for their modem and for a battery pack to help run that. And again, with our low power sensor, you can get a lot more data out of this than you could say with one of our competitors. So this is how one collaboration leads into another, and it becomes really good when it can be an off-the-shelf product from a business point of view, without needing to have huge non-recurring engineering fees or making it complicated to get you what you need. If we can work on a new project to get things to move and innovate, that's beneficial for both sides. Coming back to the Alamo Float, this is a picture of the Alamo Float here. The buoyancy engine is down here. It pumps oil, I think, back and forth, inflates a bladder, and that's what makes it float to the surface. Our temperature sensor is right up here, and then that's a modem iridium modem antenna, I think. You can see here the locations, and the color is indicating time as it progresses along its path. But what it's measuring as it's going up and down is temperature and pressure. So pressure is a proxy for depth, and you're able to get this time series of temperature through the water column as it drifts. So Hui deploys those, but they're made by MRV. And so one thing leads to another, and you learn things when they're in the ocean. We know that in the lab, we have the highest accuracy sensors. When you physically put something in the water, of course, it doesn't always behave the way you expect it to, and so profiling at high speeds, our original conductivity cell and temperature had a few problems with correlation. They still made great measurements, but they were susceptible to spiking. And so we've redesigned the sensor head. That's something that's similar to the collaboration to come get data. And we've worked with Hui, where they have a 10-meter tank where they're able to drive a double diffusion. So they have cold water at the surface that's fresh and hot, salty water at the bottom. They drive the heating and the cooling. That creates convection, and you get a very defined interface. So we were able to take this cell and lower it through, both with video and, of course, the measurements, and have come to a good conclusion in terms of eliminating that spiking. So collaboration works both ways. It can benefit us, and it can benefit our partners that we work with. And that's that.